Assalamualaikum and good afternoon. Today we are from Group 1 will be present our group project is about trust bridge model analysis. So first of all, I will introduce my group member. Start with me, Ahmad Ikraiman bin Kamruddin, Muhammad Syahmi, Muhammad Hasif, Muhammad Naim and Muhammad Fakirul Razi. Now, let's dive into the introduction and the foundational framework of our project. For our project background, we are focused on developing a small-scale timber truss model. We are utilizing 8 mm by 8 mm balsa wood as our primary material, which allow us to closely analyze structural performance and push for a high strength to weight ratio. This brings us to our problem statement. Designing a stable bridge across an 800 mm span using such a lightweight material comes with significant engineering challenge. Our main focus here is mitigation structural risk, specifically preventing joint failure and avoiding irregular buckling in the lightweight compression member. To address this challenge, we have outlined three core objectives. First, we are designing a whole truss model, drawing inspiration from historical bridge geometry. Second, we will compute the internet as a force and not a deflection using a dual approach, cross-referencing traditional manual mathematics with StatPro software simulation. And third, we will rigorously verify the structural integrity against both material failure and buckling limit. Finally, let's look at the project scope and constraint that define our boundary. Mathematical and physically, the model has a total length of 800 mm, an effective span of 700 mm, and a height of 100 mm. The structure is analyzed under two primary loading conditions: its own self-weight and a single concentrated point load applied at the mid of span. Furthermore, the project strictly prohibits the use of synthetic paints, chemical explosives, or resin, meaning our structure joints rely purely on standard fabrication constraints.
Okay, my name is Muhammad Asif and I will present about literature. For the literature review, we focus on ideal trust principle where loads are distributed purely through axial tension and compression. By using the determinacy formula m plus r equal to 2j, we mathematically prove that our bridge design is statically determinate. For the analysis, we combine manual verification using the method of join with software StatPro. Okay, for design selection, we choose the Howard Truss configuration inspired by the All East Cowley Bridge because its structure behavior is perfectly suited for balsa wood, where diagonals safely handle the compressive force. Our loading assumption follow Euro Code 1 and 5, where the safe weight act as dead load and the traffic load is simplified into a single point at mid-span and lab testing.
Hello, my name is Mark Fakirazi Damazawi and my metric number is CF240078 and I will describe or explain about methodology, first geometry, proportion and dimension. We simply follow the project specification. The total length of our bridge is 800 mm, featuring an effective span of 700 mm between the supports. This leaves a 50 mm overhang on each end to keep it securely placed on the lab testing rig. We choose a 1 to 7 height to span ratio, giving us a truss height of 100 mm, which is sit comfortably in the allowed 80 to 160 mm range. The bridge is 120 mm wide to prevent any buckling or lateral stability issues during loading. Finally, the span is broken down into 6 equal panels about 160.7 mm each, giving us a centralized joint right at the end, 400 mm midpoint to perfectly distribute the test load. For static dependency verification, before building, we had to technically verify that our truss was stable and statically determinate. We used the standard plane truss equilibrium criteria M plus R equal to 2J with 29 members, 3 support reaction force and 60 joints, both sides of our equation equal 32. This mathematically proves that our structure is completely stable and statically determinate, meaning we can solve all internal forces using basic static equilibrium. To analyze internal forces, we use StepPro. We model the geometry, define the element circularly as truss member to eliminate an moment, apply specific mechanical property. We set up a pin support at one and a roller support at the other, activate the safe wake and apply downward to point look right at the mid-span joint. To double check, the software will also run manual hand calculation using standard equilibrium and compatibility equation by tabulating and comparing step pro output with our manual vector. We were able to run a direct comparative verification, ensuring our math was flawless while accounting for minor software code discrepancies.
Now I'm going to talk about a manual calculation to find the initial force or actual and virtual force and the deflection. So this is our initial bridge design. So first we need to find the determinacy of the bridge using the equation m plus r equals to 2j. First we list the number of members, direction, and join. So we got from this equation we get that our bridge is determinate and stable. Now for the actual force, we get that Rya and Ryi is the same, which is 0.044 kilonewton, and the bottom is the initial inner force. We get it from Pro method. After the actual force was determined, we need to find the virtual force. We first put one unit load at the middle of the bridge, which is one unit downward, and then we find the support reaction where it was 0.5 unit upward for RYA and RYI, same as the actual force. We need to find the inner force, and our group use Pro method to find the inner force for this bridge. To find the deflection, we use the formula sum F times actual force times virtual force times length over AE, which is the A for our bridge is 36 millimeter square and E will be 3.4 GPa. So what we're gonna do is we put the data in a in the form of table, which is like this, where there will be member, length, force for actual force, uh, force for virtual force, and the force times length times uh, virtual force. So we sum all the F times L times mu, which is we will get 0.0590, and that value will be divided by A times E, and the deflection will be 0.482 millimeter.
Okay, Assalamualaikum and hi. My name is Muhammad Naim bin Hussein. My matrix number is the F240180. I will present about conclusion and recommendation. First, I go for the conclusion. From this project, we successfully designed, model, and analyze a small-scale timber truss bridge. We used a balsa wood with a size 6 mm times 6 mm. Our design is inspired by the historic Howe Truss design of the old East Collie Bridge. Our model features is a 700 mm effective span. Okay, through math calculation and step pro software analysis, we verified that our bridge design is statically determinate and stable. The structural analysis showed that the top middle bar, DE and EF member face the highest increasing force, which is 0.176 kilonewton, making them the most critical members to buckling. Okay, meanwhile, the vertical web members experience the highest pulling force, which is the force is 0.088 kilonewton. By using simple wood, which is balsa wood, glue, and wrapping the connections tightly with sewing thread, we were able to build a lightweight structure that minimizes balsa wood's excellent strength to weight ratio without prohibit chemical resins.
Overall, the project successfully met all its objectives by teaching us how real world designs translate into physical modes and how to balance material limits with structural safety. Okay, next I will present about the recommendation. First, we got a double up the top chart, which says member the E and EF under the absolute highest compression force. So we could glue two balsa wood stick together side by side for just those specific section. This recommendation would drastically lower the chance of the top bar buckling without adding too much overall weight to the bridge. Okay, second one is use good set plates at the joint. Okay, the wood glue joints are the weakest point of the structure. Cutting small or flat triangle out of a thin basalt sheet and gluing them over the intersection points, which is uh, we can use them as a bracket, would increase the surface area for the glue and then making the joint much harder to slide apart. Okay, the last one is incorporate light lateral bracing. While the front and back of our bridge are stable, adding a tiny diagonal cross braces between the two walls on the top floor would stop the bridge from twisting or swaying side to side when the weight is applied.